Okay, hello, I'm Christian, this is Kamil, and together we've worked on real-time tracking of items in interaction with the pick-and-place robot, and this work was done for Nomagic. So, first, the problem definition. Here you can see one of Nomagic's pick-and-place robots. It's based on production and on client's side in our warehouse. And the basic goal of the robot is to pick an item from the source container and place it in the target container. The products that robot picks are very various. They have different shapes, different sizes, different weights, and are made of different materials. And due to the variety of items and other reasons, not all of the attempts are successful. For this type of station, about 97% of them are, but what about the other 3%? So the fails are due to warehouse errors or robot errors, and the problems are extremely variant, but we've decided to categorize them into three main categories. First is item drop. Robot picks an item, and before reaching the target container, it drops it. Another is item disassembling. A robot picks an item, but during transfer between source and target container, some part of this item breaks and drops, and robot only places the part of an item. And multiple items picked, where robot picks many items, and at least one of these items is placed in the target container.
Okay, so our initial approach to this problem was that we made an assumption that having access to the precise position information of both the suction cups and the items within the video frames will be crucial for accurately identifying anomalies. This assumption was made based on the understanding that detecting abnormal behavior relies heavily on understanding the expected interactions and movements between these objects. And to validate our thesis, we implemented an adjusted version of MinVis model. This approach utilizes image instance segmentation model with additional embeddings similarity to match the IDs between consecutive frames of the segmented objects. This model doesn't require any video-based training, yeah, we chosen Mask Performer as the instance segmentation model. And train this on sampled frames from the selected videos. So here we have an example results of the performance of this model. We can see the high accuracy of IDs assignment between consecutive frames. However, as we closely examine the video, we can notice that there are X's made with tape that are also recognized as items. This is due to the fact that those pieces of tapes weren't present there when we collected the videos for training dataset. So this is obviously some kind of a limitation of this approach. Another limitation is annotating those videos is time consuming, and the process of annotation is really difficult. So we decided to abandon this approach and focus on a different one.
Yes, so we decided to move to a problem that closer resembles our final goal of anomalies detection. So there are different ways to approach this problem. And we've decided to go with multi-label online classification of the state of the robot at each moment in time, with frequency about equal to camera's frame rate. And this state we've defined is a subset of these classes. There are two non-anomalous classes, which is robot holding one item, and the no action, which means that none of the other 8 classes is present, and the other classes are anomalous. We've had data set about 1,300 labeled videos, out of which about 500 were anomalous. And on the right side, you can see distribution of classes in terms of percentages of frames. You can see that it's extremely unbalanced. So the big advantage of the definition that we presented before of these classes is that we can create labels for the model as subsets of these classes. So we basically define 3 classes, which are no action, which is no action from previously, plus items sticking out from either of the containers, because this class is extremely underrepresented. Another class is robot holding something, and the last one is something lying on the table, which was interesting is the added class of items or broken parts in the air, because per frame they all look the most like this class, and there are too few examples of this class to separate it to a separate class. And together these classes are with temporal information, so how they change in time, give a big opportunity. It's really possible to cover most of the cases of events that we've defined previously. And you can see that the distribution of classes is now much more even, and the problem is much simpler for the model, which very much increases its performance.
So after class aggregation, we were able to train the ResNet model. As an input, we used single frames of the videos, and the output was the confidence score of predictions for each of these classes. So on this video, we have on the left we have plots of confidence for each of the classes, for each from the classes, and at the beginning of each attempt, no action class is predicted as the one with the highest confidence score. When the item is picked by the robot, it changes, and the robot holding something class is predicted. And when something lands on the table, the corresponding class is detected. We can see also the vertical lines indicating the moment of the anomaly in these plots.
Okay, so how can we improve that? Basic idea is to add memory to the model. And we've decided to use an architecture called LSTR. Because of lack of time, I won't go into the details, but in a nutshell, it just applies a transformer to features extracted with a backbone and with frozen weights, so for example ResNet. And here we can see a sample prediction in case of an item drop. So, but what's the comparison between LSTR and ResNet? Here you can see in both tables, in each cell, on the left side of the slash is LSTR score, and on the right side is ResNet score that was used as the backbone for this particular LSTR. In the top table, there are compared 4 settings of backbones. From the top, it's ResNet with weights pre-trained only on ImageNet and then frozen. Another row is ImageNet with ResNet pre-trained on ImageNet with fine-tuning on our dataset. Then it's ResNet pre-trained only on Kinetics 400 dataset. And the last one is ResNet pre-trained on Kinetics 400 dataset with fine-tuning on our dataset. And in the bottom table, you can see metrics per class for the best performing model, which is LSTR with ResNet pre-trained on Kinetics 400 with fine-tuning. And you can see that metric-wise, there's not that big of a difference between LSTR and ResNet when we use fine-tuned backbone. But the big advantage of LSTR comes as its robustness. LSTR scores are much more confident. Here's an example of predictions in time of class something lying on the table. The predictions keep closer to zeros and ones. And it's also much more resilient to threshold selection. Here is on the right is example of F1 score versus threshold. And this is very beneficial for production use. And we can see similar pattern emerging across all the other metrics as well.
Okay, so to be able to verify how useful our solution is in the production, we defined 3 anomalies based on the states that were predicted with our model. So those are item drop, partial drop, and long lying on the table. They are pretty straightforward. So item drop happens when we switch between a robot holding something and something laying on the table. Partial drop happens when additionally robot still holds something, and long laying on the table happens when there is many consecutive frames when something is on the table. And to evaluate our efficiency in recognizing these anomalies, we collected dataset from the videos recorded in May. We divided this dataset into three subsets. One that contains videos without any anomalies. One set that contains videos with anomalies that we aimed to detect with defined states. And the last one contains all possible anomalies that can happen. And based on the results, we approximated score on production. We aimed to recognize as many cases of anomalies that we wanted to detect as possible, which can be seen in recall value metric. And we were able to maintain high precision as well. So yeah, I think that's it. If you have any questions, feel free.
Let's thank the speakers.